Hi, ladies. Today you're going to need your notebook and your textbook. And the lesson is from page 178 to 181 in your book. And we're talking about earthquakes. So hopefully you already know why this is funny. If you don't, hopefully you'll know why at the end of this lesson. The beginning, a lot of it is going to be review from when I saw you 2 weeks ago. But all right, let's get started. So, what causes earthquakes? The movement in the mantle causes rocks to move in one of three directions. So, if rocks can't move, the pressure builds up. That's potential energy. When enough energy builds, the rock will snap, just like anything. And that will be the kinetic energy. You feel that kinetic energy of the rock as an earthquake. The more potential energy builds up, the more kinetic energy is released, and the bigger your earthquake is going to be. This is just a guy explaining elastic rebound. So it's basically if you bend a stick, eventually it's going to reach a breaking point and it's going to snap. The same thing happens with rock. So this is the elastic rebound demonstration. So this man is holding a ruler, but pretend the ruler is actually rock, and rock bends. And the more you bend it, the more pressure builds up until it can't take it anymore and it snaps or moves. I'm just going to forward it a tiny bit.
And bend it too far, then, of course, what's going to happen is it's going to fracture. So that was the limit.
That's it. That's all elastic rebound is. All right, so you need to know that there are three main types of faults. All earthquakes happen at faults. Important, all earthquakes happen at faults. There is no earthquake that ever happened that didn't happen at a fault. So the first type of fault we'll talk about is a normal fault. It's also called a slip fault because what happens is you have the pressure is pulling apart, kind of like a divergent boundary. It's pulling apart, and so gravity pushes one side down, it slips down. A normal fault, it pulls apart, the rock are pulling apart, and one side slips down. A reverse fault is the exact opposite. The pressure is pushing in, and one side actually slips up. And then the last one is a strike slip fault, where the pressure, they're going in opposite directions. So these are very like the boundaries. They move very similar to the boundaries, right? A normal fault would be like a divergent, a reverse fault would be like a convergent, and the strike slip fault would be like a transform boundary. So normal faults, I told you the pressure is pulling out. It's also known as a slip fault because here, once the rock is being pulled apart, gravity will just push it down. And here are some real life examples so you can see that these aren't matched up. So you can see that one side went down. Here's another one. The reverse fault, I told you, with the opposite. Your pressure is pushing in and one side actually goes up like this. I know someone's asking, how do I know if I saw that in real life? I'm not a geologist, so I really honestly can't tell you. But I can see it. I can't tell if it's a normal or a reverse, but I can see that a fault happened because nothing is lined up. All right, and then you have the strike slip. They're moving past each other. You can see it here real well. It runs right through here, and the road is divided. It's another road. You see the L, the letters don't line up. So the most famous fault in the United States is the San Andreas Fault. You need to know that, the San Andreas Fault. This is a very long fault. So if you look over here at California, This fault runs all the way up. But all throughout here are little faults. There's little faults, little faults. So they have earthquakes constantly. There's little earthquakes that they don't feel. There's little earthquakes that they feel but are nothing, they don't think about anything. But imagine if this whole thing slipped. Normally, a part of it will slip at a time and another part of it will slip, and you feel them as earthquakes. But when the whole thing slips, you are going to have a major earthquake. This is what it looks like if you're in, not in the urban parts, just out in the fields. This is what it looks like. And this is just showing you the Earth Science Reference Table. You can see the San Andreas Fault here. Very big. This fault actually lies on a boundary, which is what gives it so much energy. So you have the Pacific Plate turning and the North American Plate turning in opposite directions, and the fault is in the boundary. All right, seismic waves. We did speak a little bit about this, and we had people demonstrate. When a rock breaks, causing an earthquake, seismic waves are released from its focus. The focus is the point inside the crust where the earthquake first happened, right? And then if you were to draw an imaginary line from the focus to the Earth surface, that would be the epicenter. And if I'm going too fast, just pause the video, rewind it, whatever you need to do. All right, so I didn't do the graphics right here, but that's okay. So seismic waves, the break in the rock releases energy in the form of waves. Primary waves, this is our first one. They are the fastest, so they're the first ones on the scene, and they are transverse waves. So they go up and down like this. They're able to travel through solids and liquids inside the Earth. Then we have our seismic waves. They're the secondary waves. They move slower than P waves. And I put invisible because I don't want people to think that you can see them. You can't. They are all invisible. They're compressional waves, but they are only able to travel through solids. The most destructive waves are the surface waves. They are the slowest and the largest waves. And they're the most destructive because they move the Earth's crust. So here, this was the animation that I showed you in class. So you can just maybe take a look at it again. And you can see the P waves, they go through the solid and the liquid outer core, but it's at different speeds. And you can also see, let me move that back. The light blue bounces right back as soon as it hits that liquid. As soon as it hits that liquid core, it bounces right back. It does not go through liquid. It goes down the side. The P wave, the dark blue, hits the liquid core, starts going at a different speed, then hits the solid inside the liquid core, and starts going at another speed. This is how scientists know what's in the Earth. Okay. All right, so I have these two videos for you. This is a very short video. I have no idea how they caught it on camera. Earthquake. Did you miss it? Yeah, it's crazy, isn't it? And this one is just a bunch of earthquakes that were caught on tape. I'm showing you these videos because I want you to see the destructive force of an earthquake because we don't really have them here. The surface waves are what's causing that. You're going to see the roof collapse.
The mall. So you can see the rumbling there on the street. The building just fell. People can't stand up. It looks funny that the bike fell over, but the road is literally moving from side to side. Just going to fast forward a little bit. See that? You could possibly drown or something like that if you're not a strong swimmer. Nature is a strong force. The surface waves are so destructive because they break foundations. I'm going to skip forward a little bit if I can find. There we go. This guy doesn't know what to do. You can see the lampposts and things are shaking. All right, I just wanted to show you a little bit. All right, so let's go back. Earthquake measurements. Scientists study earthquake and seismic waves. They study the earthquakes, like where they started, the epicenter, the focus, and they study the seismic waves. The instruments they use to record seismic wave is called a seismograph. The seismograph produces lines on a paper that measure earthquake energy. The bigger the line, the greater the energy that was released by the earthquake. You've probably seen a seismograph in action before. We call the energy that is released the magnitude, right? So the greater the energy is released, the greater the magnitude of that earthquake. Earthquakes are measured in units of magnitude. So it was a 3.2 magnitude earthquake. It was a 5.9 magnitude earthquake. And this is an example of what a seismograph. This is a very simple seismograph. Now they have them hooked to computers and everything. Will give you instant readouts of the magnitude. But this is essentially what it's doing. You have the ball with a pen or a marker just suspended in the air, and then as the earth moves underneath it, it makes marks on the paper. All right, that's for tomorrow. So your homework for tonight is here. I have a sheet for you, and you just submit it through Google Classroom, and anything that's highlighted in yellow, I'm going to make a copy for everybody. So all you have to do is click on it, and you can just write your answer in and then submit it. Okay? All right. Don't forget, I would like for you to re-watch this video. I need you to get these concepts down because you are going to have a test. You are going to have a quiz. Take your notes. Pause the video, rewind the video, whatever you need to do. All right. When you're done, start your homework.